Thanks so much, Mangesh. Thanks so much, and thanks so much for the invitation. Like I mentioned earlier, I was also a member of AAA 30 years ago when I was a college student in St. Xavier's. So it gives me great pleasure to be part of AAA again after such a long time. So thanks so much, and I'll now start off with my presentation. Yeah. Uh, Please let me know if everything is fine. Can you see my presentation? Yeah, great. So actually, I slightly changed the name. It's become the exciting world of exoplanets, which I talk about. And like Mangesh mentioned, I'm in Hyderabad in Maulana Azad University. And in case you want to get in touch with me, here's my email, very easy to remember. So you can always come back to me if you have some questions. So let's start off that as of September 2022, there are 5,000, more than 5,000 confirmed exoplanets in 3,804 planetary systems, with 833 systems having more than one plane. Now, first of all, let's start off with the main thing is why do we look for exoplanets, right? So this is one of my favorite quotes. This is a quote by Carl Sagan, which is part of his movie as well as the book Contact, where there's a dialogue in which it's explained that the universe is a pretty big place. If it's just us, seems like an awful waste of space. So this was the kind of justification that was given for looking for life, intelligent life in the universe or life in the universe. And if you want to look for life in the universe, the first thing to do is to look for exoplanets. Looks for planets outside our solar system. Then you can look for things like habitability, conditions on them, characterize their atmospheres, and based on that, you could actually look for actually life. So that's how the thing starts off, and this is the first step to doing that. So let's see, what is the definition of an exoplanet? So an exoplanet or an extrasolar planet is a planet outside the solar system, which doesn't belong to our solar system, and that's an exoplanet. Now, obviously, science fiction movies, books have had various kinds of. This is Tatooine, where you have two suns. This is science fiction, but obviously, this has been one of the favorite topics for science fiction to talk about various kinds of exotic exoplanets that could be possibly there in our universe. So, let's start off with in the year 2019. Many of you all may be aware, but one half of the Nobel Prize for Physics was actually awarded to Michel Mayor and Didier Colletz for their discovery of the first exoplanet orbiting a sun-like star. So this was the planet 51 Peg B, which is about 48 light years away from the Earth. This is when Didier himself was a PhD student working with Michel Mayor, and that's when they did this thing. Now, in principle, if we look historically, this is not the first discovery of an exoplanet. The first one was actually around a pulsar, which was in 1991. This discovery is actually of 1995. But the thing is that the earlier one was not a sun-like star, it was a pulsar, and probably this one was more exciting because it was a sun-like star. So actually, if you look back in it, way back in 400, 500 years ago, it was already proposed by Giordano Bruno, that the space we declare to be infinite, and that there are infinity of worlds of the same kind as our own. So in short, this idea of looking for exoplanets or looking for worlds other than known was a very early idea, which actually people did find very interesting and intriguing, right, for themselves. And but discovering it was obviously not a very easy job. And this was one of the most eagerly awaited discoveries by people of actually looking for exoplanets, because there were various searches which were on for decades. Many teams, many stars, different techniques were actually used to look for exoplanets, but they were without success. And that's essentially because, why could they be possible is either the techniques were not sensitive enough, or there was even a proposition as perhaps there are no planets after all, or what were the other kind of reasons for not detecting. The first confirmation, like I mentioned earlier, was for the pulsar. And this is an earlier date. Now the detection techniques, there are essentially 4 detection techniques. I'll talk about 4-5 detection techniques. It's actually literally like finding a needle in a haystack. So there is the method which was used by Didier Colletz and Michel Mayor, which is the method of using radial velocities, which is still a very popular method. There's the transit method, where you actually look for light curves of stars. using space-based telescopes as well as ground-based telescopes. Then people also used another technique called micro-lensing and timing, pulsar timing arrays, etc. There are various methods of actually looking for exoplanets. So let us look at all these methods. So the first method is the radial velocity technique, where typically if you have a host star and you have a planet going around there, so what basically happens in such a case is that if you look at it, see, this is a star with a planet going around that. So what happens is the star and the planet, they form a two-body system, and they actually go around their common center of mass, which is this, this green plus sign, which you can see over here. So essentially what happens is that because of that, the star itself appears to wobble, right? Because the star is going around this center of gravity, and the planet is going around here. And therefore, there's basically a wobble in the star's position as well as in its velocity. So you see there's a point when the star is coming towards you, when the star is going away from you. And therefore, if you look at it like an animation like this, we know that from the stars you can actually observe spectra or spectral lines. Now, spectral lines are indicated over here. You have the continuum, which is ranging from a whole range of wavelengths, and you have this spectral line, which is the dark black line. And what happens is, as the star, this is Doppler effect, which you all of us are aware of. Doppler effect tells you that if you have a source of light moving away from you, the wavelength shifts towards longer wavelengths. If it's moving towards you, it moves towards shorter wavelengths. And therefore what happens is, as the star, this is the star, it's moving away from us, you see it's moving towards longer wavelength. As it moves towards you, it's moving towards shorter wavelengths. And therefore, if there's a certain spectral line, which you were to observe at this, the dashed line. The dashed line is what we call the rest frame wavelength of the spectral line. So this is the actual wavelength of the line. But as the star is moving towards us and away from us, because of that, you're going to actually have a shift in the spectral wavelength. So you are going to find a delta lambda or a shift in the wavelength of that light moving from red to blue, right? And that is essentially what you have to detect. You have to detect the shift in wavelength. And therefore, if you actually see that as the star moves, you will have this shift in wavelength, right, as the star is moving, and that's what you actually got to detect. So if you look at this in this case, you can see that in terms of kilometers per second, you can see that while the star is moving away from you, you have 61.45 approximately, 61.25. So you have this very small shift in wavelength, right? And the problem is you need to detect or measure this shift in wavelength. This is not a very easy thing to measure. So if we were looking at our solar system from outside, this Jupiter causes just a 13 meters per second variation in, this is in kilometers per second, okay, note. But Jupiter causes a variation of about 13 meters per second in the in the velocity of the sun. The Earth causes only 0.1 meter per second. So if you were to look externally at our solar system, you could probably detect Jupiter, but you definitely won't be able to detect the Earth. Now, the Very Large Telescope in ESO has a spectroscope called HARPS, and HARPS actually has a measurement limit of about 1 meters per second, right? So this is the kind of accuracy you need with your spectroscope, so that you can actually detect a wavelength difference or a velocity difference of this kind, right? So this is the one at ESO 3.6 meter. The other problem with the radial velocity thing is obviously it depends upon the orientation. How is this exoplanet's orbit oriented towards your orbit, right? And therefore what happens is that supposing there's a tilt of the axis, right? This is the the plane of rotation of the exoplanet, and therefore what happens is that if there is it depends upon how are you oriented, where is the observer looking at the system form. For example, if the observer is over here, you will see a very nice shift in the wavelength, but otherwise you are basically just going to see a projection, right? And therefore you're just going to see a projection of the inclination, and therefore it obviously depends upon how is the tilt of the the plane of rotation of this exoplanet to your angle of observation. Depending on that, you will be able to see the a given Doppler shift. Rather, you're going to see a projection of the Doppler shift, right? And that will depend upon the orientation. And therefore, what happens is with the radial velocity technique, that you do have this problem that you do not know exactly what is the tilt. You can measure the velocity, but you do not know the tilt of the axis. And therefore, your measurement of mass, which you get for the object, will be an m sin I. We do not know what is I, right? What is the inclination of the orbit. And therefore, typically, like in this method, what they did, this is Michel Mayor Didier Collet's. So basically, you are measuring a delta lambda, a shift in wavelength by the lambda, which will give you the radial velocity divided by the velocity of light. And therefore, like I mentioned earlier, the tug of Jupiter is about 12, 13 kilometers per second, which corresponds, if you were to check it in terms of wavelength, it would be a shift of barely 10 power minus 14 meters, which is about 10 power minus 5 nanometers. So that is the kind of accuracy you need for your spectroscope so that you can measure something like this. I'm mentioning these numbers because it's very important for us to appreciate the kind of precision required in this measurement. And therefore, when they actually when it was actually confirmed in 1995, the team, when they detected the exoplanet, they found it had a 4-day orbit near the star 51 Peg. And the other important story while they observed it is that they noticed that this object had twice the size of Jupiter. It was 7 times closer to the star than Mercury it is to our sun, and therefore it was a very strange kind of object. You had this giant planet which was very close to its star, and therefore it was also very confusing as to how could you have such a system, right? And was it some kind of planetary migration that the planet formed somewhere else and then it moved away, or what was the actual picture, right? How do you actually have such a massive planet sitting so close to its star? And so therefore planetary migration is also a very well, yeah. Yeah, one sec. Let me just see. What is the notification? Okay, okay. One minute. Okay, that one. Okay, okay. No problem. Fine. Okay, no problem. So actually, around those time, people were already considering whether in our solar system itself, did the planets migrate, right? So this was actually validation for possible planetary migration, and we know that there are some very well-established theories of formation of our solar system, where we actually do consider the Grand Tack, where actually there has been migration of the planets of our solar system. That means they did not exactly form at the positions where they are today found, but they formed at other positions and they've kind of migrated, right? So studying other exoplanets or other planetary systems also gives us very good insight into the formation of our own planetary system. We don't have the time to talk about this too much today, but essentially it actually builds your awareness on what is planetary migration, for example. Now, till about 2012, this radiation velocity method was the standard method used to look for exoplanets. But obviously, when the group had to actually validate their results, they had to actually show how their results were, they considered all kind of other errors that could possibly cause this thing. And for example, the biggest problem with the radial velocity technique is the problem of false signals. So basically what happens is you have a broadening of the spectral line, and you say that the broadening is happening basically because of the wobbling of the star, because of the presence of the planet. But in principle, you could have other reasons also for broadening of the spectral line. For example, it could be magnetic fields, it could be other kinds of stellar activity which could actually cause it. And therefore, the team actually had to give very substantial evidence more than their result, their observation. They had to give very substantial evidence. Why do they believe that their result is because of the presence of the planet and not because of other methods? So this is a very laborious task which they did. They're successful in doing it. And the transit method, like I said, is also a very good method to actually do it. The good idea is that the transit method actually gives you a very good measure of the mass to the accuracy of m psi 9, right? You don't know the inclination of the orbit, but otherwise the radial velocity is a very good technique to actually measure, find the presence of this thing. The other method which is used more popularly to look for exoplanets is what is called the transit method. Now in the transit method, what happens is you have the planet coming in front of the star, right? And therefore what you see here, this is called a light curve. So the brightness from the star, you can see, shows a certain dip, a fall in the brightness when the planet comes in front of it, right? Because the planet obscures the view of the complete star, and you are going to cut off this light, due to which you get this drop. And this is what is called the transit method. Now the transit method, the problem with the transit method is that this depth which you are going to get of the light curve is a ratio of the square of the radii of the planet to the star, right? Because that is the ratio of the difference in the area, right? So this is pi r star squared, which is the whole area, and this is pi r planet squared, which is the area of the planet. So the ratio of these two will tell you what is the depth. Now, if you were to take it for the Sun Earth system, right, and you take the ratio of the radii of the Sun to the radii of the square of the Earth and square it, you will get a ratio of 10 power 4, right? So, therefore, that basically tells you that the dip which you are going to get is going to be of a factor of 10 power 4, right? This is going to be that small, the dip. So it's something like saying that supposing you had 10,000 light bulbs on, only one light bulb will get off, and you need to detect it that one light bulb has gone off. That's the kind of precision you're going to need to require in your photometry when you're measuring the brightness from that star, right? So that's the problem with the transit method, and therefore, since it has to be done with this kind of an accuracy, there were basically two space telescopes which were sent to actually observe this, right? So one of the most popularly known one is called Kepler. So Kepler is one of the satellites which was actually sent to look for the light curves to search for exoplanets. What Kepler basically did is it stared at one part of the sky, okay, and it kept looking for the light curves of stars in that area. And for example, look at this. This is an example of a hot Jupiter. This is a planet of the size of Jupiter going around a star, and you can see that this is the variation in brightness you're getting. So when the planet comes in front, you have a dip in the brightness, then the planet goes behind, then again the planet comes in front, you get a dip, and you go this. So you can see that this dip is literally a 1% dip, right? You have, if you were to normalize that the brightness of the star was 1, you would get a brightness of 0.994, which is what happens when the planet comes in front of it. So this is the kind of accuracy you would require to actually detect it, right? So I go back to the point which I said right at the beginning, that exoplanet discoveries took so long basically because the kind of precision which was required in the measurement of, for example, radial velocities, or for example here in the brightness of stars, you need to measure a dip of this kind, right, so that you can actually detect the exoplanet. And that was a difficult thing to do. So Kepler, like I said, is a space-based telescope, so you do not have any interference coming from the atmosphere, and therefore Kepler could accurately measure things like this. So typically what is done with Kepler data, that you need to have at least 3 transits. You need to have observations of at least 3 transits to confirm the presence of a planet. The other thing is from the dip, the size of the dip, you again use the same formula, rp squared divided by r star squared, right? That is the ratio. That will tell you what is the fraction of the dip, and based on that you can find out what is the size of the planet. In some cases you have more than one planet going around the star, and you will get multiple dips. So with that you can get the number of planets. The orbital period is obviously from your observations. For example, here you can see this. This has an observation period of about 2 days, the orbital period. And the inclination effect. That's the other problem which you have with this. But this is the kind of observations and the data you get from Kepler. Here I have another example of an exoplanet which was observed by Kepler. This is VAS 33b. Again you can see that this has a depth of only of 0.03 magnitudes. But since this is the Amateur Astronomer Society, I added this thing because this is a plot which has been got with a 16-inch telescope. Okay, this is in 2016 using a 16-inch telescope. People actually managed to get this kind of an accuracy. Obviously, you need to have a good sky so that you can get a thing like that. But they actually managed to get it for this planet which has a transit period of 1.6 hours and a depth of. So in principle, there's still a lot of exoplanet research one can do with smaller telescopes, right? For example, like the 16-inch telescope. Obviously, you need a good photometric night to be getting accuracy of this kind, but in principle, it is doable. Another method of actually looking for exoplanets is the method of microlensing. Now, what is microlensing? If, for example, I have a star over here, right, and I have a planet over here, what happens is that because of the gravitational effect of the planet, it actually behaves like a lens, okay? So gravity actually can behave like a lens, that is, it can bend light. So what happens is when you're looking at the position of this star, you're actually going to have it lensed and the position of the star will slightly shift. there'll be a change in brightness. Okay, and typically what happens is you have something like this. So this is the star with the planet, and this is the kind of brightness effect you will have. So you'll get this kind of a glitch, and you'll get a bump coming like this over here. This is typically the kind of light curve you are going to get if there's a micro lensing effect. Remember, I showed you what it should look like if there's a transit, but this is the kind of signature curve you will get for a micro lensing effect. So in case you have a star with the planet, this is the kind of effect you get. So it's again shown over here, where you have this loop coming up over here. You have a slight, what happens is basically there's a slight magnification in the brightness of the star. So you'll see a slight bump coming up over here. Suddenly the star looks a little bright and then it comes down, okay? Because the star gets over focused and then it comes out over there. So this is the kind of observation you will have if you have a micro lensing effect. Another way of actually looking for planets is using the method which is called direct imaging. Now what is direct imaging is supposing you have a star over here. This is a star which has 3 exoplanets. There is B, C, D. What happens? The A number goes for the star, okay? So for example, when you say 51 peg B, you're basically, the A is the star and then the exoplanets come as B, C and D. So here you have a star which has this planetary system. It's obviously very, very difficult to do direct imaging for the simple reason is that the star is going to be much, much brighter than the planet. So often the contrast could be with a factor of say 10 power 9, right? So for example, if you were to look at the Jupiter Sun at a distance of about 5 parsecs, angular separation is less than 1 arcsecond, and therefore looking for it would be very difficult, right? Because the star is very bright. But it is best if the planets have wide orbits, right? Particularly massive, precision Poisson, then you can actually try to look for, to try to do direct imaging. Like I told you, because the star is so bright, we need to think of a way around the problem. How can you actually do that? So one method is this, which we anyway use. SOHO spacecraft is a spacecraft which specifically observes the sun, right? And what it basically does, it uses something called a coronagraph. So what it does is while it's observing the sun, it puts a kind of a cover to cover up the sun, and it looks at the corona of the sun, right? This is the corona of the sun. And with that you can actually look, and the corona of the sun is very hot at a temperature of about 1,000,000 degrees. So if you can observe it, you'll actually see it like this. Now nature itself gives us these opportunities. For example, when we have an eclipse. When you have an eclipse, the moon comes in front of the sun, right? And that's when you see what is called the butterfly effect or the diamond ring effect, in which you can see the corona of the sun, right? So you cover the sun and you see the corona of the sun. So typically this is what SOHO does, right? If you want to even look at, this is an example of an image of Saturn, where you can actually see the rings of Saturn and a moon by using a coronagraph. So a similar thing can be done for exoplanets. So I can show you this example over here. Here you have a nice bright star. But you see, I cover the star and you can see the planet which is there, right? I'll repeat this video so that you can see it. Let us see it. So here you have a star. You do not see the planet. But if I cover the star with a coronagraph, which you can see in the video, then what happens is you can actually see the planet, right? So you cover the star and there, voila, you see the planet. So this is the coronagraph, and such a thing has been used on very large telescopes, for example the VLT, where you actually try to look for planets by covering the main star. So here you have images of using Keck, using the Keck telescope. You actually have images where you cover the star, and here you can actually see the planetary systems B, C, D. For example, here also you have a VLT infrared image of a young planet going around a brown dwarf star. You have examples over here on HST. Also the Hubble Space Telescope, that is HST. There is a coronagraph and it comes around the planet, okay, and you can actually catch this thing. So here you have an example with Fomalhaut. This is a star for which you can actually use it, compare it, and this is compared to our solar system, right? It's a reasonably similar planetary system compared to ours. So this is also another example. So you're actually going to the accuracy of about 20 astronomical units. I will repeat, astronomical unit is the distance between the Earth and the Sun, which is 150 million kilometers. So this is actually detecting planetary systems at about this distance, right? About this, or a little larger than that. So Pluto is at a distance about 40 AU away from the Sun. So you're looking at planetary systems around this distance using direct imaging, right? This is another very well-known system, Beta Pictoris, which also has its planetary system, which can be observed using the VLT, the very ledge. So I actually had already shown you a Kepler picture, but like I showed you that the important thing was to obviously observe exoplanets from space. So the Kepler mission was actually launched in 2009. It has a primary mirror of 1.4 meters. I'd already showed you an image of this thing. So if you actually look at the detection methods, the red one is the radial velocity, the blue one is the transit method. So you see that the radial velocity method has been consistently used to look for exoplanets. But after the launch of Kepler, there was obviously a very big boom in the number of exoplanets detected. But what Kepler, like I told you, it just looks at a certain field of view, looks at a certain part of the sky, and this field of view is out of the ecliptic, right? And it is selected in the Cygnus and Lyra constellation. So it just keeps looking at this, right? So this is about the size is about the size of a fist at arm's length. That's about the size of this field. Okay, that's what Kepler did, and that has given a very large number. But after some time, what happened is there was a certain problem with Kepler. There was a problem with its reaction wheels. Okay, it happened in 2013, and therefore then Kepler slightly changed its mission. It could not exactly continue the way it was, and the sequel to this is still Kepler, but it's called the K2 mission, which then the field of view actually increased because you could not target the same part of the sky. It kind of increased it, and but you still have access to many more sources. But finally, Kepler retired in 2018, right? Then that's when it went dysfunctional. After that, another in 2018 itself, back to back, you had another exoplanet survey satellite. This is called TESS, which is the Transiting Exoplanet Survey Satellite, which again looks for exoplanets exactly the same way like Kepler does, but it does it for an area 400 times larger than that observed by the Kepler mission. So this is the TESS satellite. So one can actually, we do not have the time today, but one can actually, what's an interesting thing in astronomy nowadays is a lot of astronomy data is freely available on the web, right? So for example, Kepler data, TESS data, it's all available on the NASA's MUST website. And therefore what you can do is you can actually access Kepler data or TESS data and actually use that to do your own analysis, do your own projects, and make your own studies, right? So I myself have been done a lot of sessions with students on actually how to, we don't have the time to do that today, but you can actually see on how to use Kepler data and TESS data to actually analyze it and look for this thing. And like I said, these are very doable projects because the data is all available online. You just have to work with it a little bit so that you get an idea of how to handle it. If you do that, that'll be good fun. So a lot of, for example, here I have an example of an astronomy student in Canada using Kepler Space Telescope. He's from the University of British Columbia. He actually managed to discover 17 exoplanets. This is basically because the Kepler and TESS data is very large amount of data, which is obviously much more in proportion to the number of working astronomers, right? So in today's times, there's a lot of astronomy data available, and the number of astronomers are not so many to handle all that data. And therefore, for example, in this case, I just showed this for the benefit of students. This was about in 2020, where this student, he was a PhD student who actually discovered evidence for 17 new exoplanets using Kepler data, including a roughly Earth-sized world found in the habitable zone. So, in short, people can actually do that. Along with that, there are a lot of citizen science projects. Now, citizen science projects are things which non-astronomers or non-scientific, people can also do. So what happens is, like I told you, the same reason that because we have so much of astronomy data available compared to the number of working astronomers, a lot of data sites in astronomy have opened their data for citizens. So this is basically for citizens who are interested in science and who would like to contribute to astronomy in some way or the other. So what happens is that there are various citizen science projects, like there's one called Planet Hunter. There are many more. If you're interested, you can get in touch with me or with some other people who are involved. And you can actually do various citizen science projects to actually look for analysis of Kepler or test data and actually look for more exoplanets, etc., compared to the one that's already discovered. Even some of the work can be done. For example, this is an example of radio emission from a red dwarf star indicative of star-planet interaction. It's not only the optical wavelengths, but even people have been working even in other wavelengths, for example, the radio wavelength. Now, exoplanets are obviously very, very interesting to everybody, and a whole lot of exoplanet missions have been done. For example, Hubble was not exactly an exoplanet mission, but Hubble has observed a lot of exoplanets, right? Spitzer, this is an infrared telescope. This has also looked a lot about looking at very young stars and their planetary systems. Kepler test, these are all, TESS is still operational. These ones are, these two are not operational. Hubble is also still operational. And now we have the era of Webb, and then we'll have Plato. We have various other missions which are there to add on to our study of exoplanet missions. Now there are various type of exoplanets if you actually look for it. Some of them are gas giants made up basically of gas. Some of them are, gaseous worlds by sign of Neptune. Neptune-like, there are super Earths, potentially rocky worlds larger than the Earth, or there are terrestrial ones, quite like the Earth. If you were to actually look at the demographics, what kind of exoplanets you find, you can see that these are the hot Jupiters are the ones which have much larger to the Earth, say 10 or 30 times larger than the Earth, with orbital periods lying between 1 to 10 days. These are hot Jupiters. You could also have coal class giants, which are huge, but they have longer, periods. You could have these rocky planets, which have a period of about 1 to 100 days, or you could have lava worlds. And there are various methods. You can see the colors are over here not very clear, but you can see that there are various different techniques are more sensitive. For example, the radial velocity technique, which is in light blue over here, it's very good at detecting exoplanets within this range. But for example, the transit method is very good for observing exoplanets within a few days, because that is easier for you to observe rather than long days. And so there are various. So Kepler has done it in a full range. Kepler has given us data in the whole range, and you can see that there are different techniques which are sensitive to different kinds of methods of detection, right? In astronomy, we always have to be very careful that our methods of detection are always sensitive to certain kinds of objects, and therefore we may actually misunderstand their populations, right? For example, we often it's obviously easier for us to see brighter stars, right? More massive stars are brighter, we see them more often, right? And these more massive stars which are more brighter, they are often binaries, and often therefore we all feel that most of the stars are binaries, right? But that's not true. That's an observational bias, because we typically see massive stars and we get this idea that most stars are binaries, basically because our observational bias makes us see the massive stars, which are generally binaries, right? But that does not mean that all stars are binaries. Similarly, in this case, you can see that depending on the kind of method you use, you will have a certain bias in the kind of population you are looking at. Now, if you look at Kepler discovery space, you can see that Kepler basically observes planets with orbital periods less than 400 days and sizes larger than Mars. That's what you get. If you see the yellow-red dots, so the red ones are again with transits, and the blue ones are with radial velocity. So with radial velocities, you will be able to observe these kind of objects more. With Kepler, you will see this. So with Kepler, you're getting it between the planet radius of Earth and Neptune. You also get these ones, the larger ones also. And the problem with Kepler, with with radial velocity, is you're typically going to get more massive exoplanets, because they are the ones which will cause a larger wobble, right? If you want a larger wobble in the position of the sun, that will happen if the planet you're talking about is more massive. And therefore, you will see it typically for Jupiter-like planets. But you will not see it too much for an Earth-like planet, because like I mentioned earlier, the Earth will give a very small wobble of barely 0.1 meters per second for the sun, which is not going to be very detectable using our radial velocity spectrographs, right? So therefore, you're going to have a slight bias in the way you are observing things. Now, if you actually look at the size distribution of planets for stars similar to the sun, right? This is typically for stars similar to the sun. You will see that you see quite a few planets in this kind of a range. If you take the planet size, the Earth is 1, you'll see you'll have many of them between 1 to 1.4, and then you'll have even the larger sizes coming like this, right? And so it basically shows us that the Earth-sized planets may be actually the most common type of exoplanets, unlike what we got from our observations. You remember, if you look at these observations, radial velocity technique will basically show you more Jupiter-like exoplanets. So earlier, people did observe more Jupiter-like ones. But if you actually look at planets for stars similar to the Sun, you'll actually see, no, the peak is coming somewhere over here, right? It's about the size of the Earth or double the size, 2-3 times. So the most common planet size are those with radii between 1 to 3 radii of the Earth, what we call Earths, or what we call even super Earths. If you Another very important thing which we need to do for exoplanets is we plot what are called mass radius diagrams. Why are mass radius diagrams important? If you just think of what is the formula for density, density is mass upon volume, right? So volume is 4 by 3 pi r cubed, right? So if I actually do a plot of mass versus the radius, here you can see this is a logarithmic plot. So therefore what you see is that mass by radius in a way is a measure of density. So it actually tells you the density of the planet. So if you measure the mass and its radius, you can infer the density. So the exoplanet's composition you can get from its mass and radius. And therefore you can see that here, these are the hydrogen ones, the hydrogen helium ones. These are the ones with magnesium silicon, and the iron ones are the ones coming over here, right? So typically if you make these mass radius plots, you will be able to infer the composition of the exoplanet, right? So various studies like this are done. This is of radius versus the period. This one is mass versus the period. And you can see that there are certain populations or certain groups of exoplanets which do exist, right? If you want to actually estimate the number of Earth-sized planets in our galaxy, right? Approximately, we know that we have about 100 billion stars. Actually we have about a 400 billion, but we know that very hot stars, for example O-type stars, will not manage to have planetary systems. So if we typically look for stars which have spectral type of F, G and K type, there are about 100 billion stars in our galaxy. And if you can say that they have, if you say about 1/3 of them have planetary systems, you'll have about 30 billion Earth-sized planets in our galaxy, right? If you include super Earths, then there could be 100 billion. So the idea that planets of roughly the Earth size are so numerous is one of the most important discoveries of modern astronomy. Now the next job is, how do you actually look for it? But if you actually look, like I say, this plot I'd already showed you, if you look in terms of radius of the Earth, you'll see that 1 to 5% of the planets have this, while a bulk of planets have this size and these ones. So solar system planets are not so common, the kind of distribution we have. If you actually also look for the orbits of extrasolar planets, you can see that this is the typical distribution of orbital distance. If we plot our solar system planets, we sit somewhere like this over here. This is the eccentricity versus orbital distance. This is where our planets sit, but you can see that the other ones we have discovered we are seeing more eccentric planets. Our solar system planets are not very eccentric. The most eccentricity you have is about 0.2. But otherwise, the bulk of the planets have a very low eccentricity. That means their orbits are very, very circular. But we actually, through extrasolar planets, we discovered many which have larger eccentricities. That's another observational bias. So if we were to plot actually the orbits of extrasolar planets, most of the detected planets have orbits smaller than the Jupiters, like the one even which was done by Didier Queloz and Michel Mayor. And planets at greater distances are harder to detect with the Doppler technique, right? So you have a certain bias coming in this. Orbits of some extrasolar planets are more elongated than those of our solar system. We can also ask a question is, how many of these planetary systems are multiple planets? And if you actually look at most of the planetary systems which are detected, some stars do have more than one detected planet. Again, part of it is an observational bias. We do not get to see all these things, basically because this is for 0.1 times mass of Jupiter, that, and so you have, for each of these systems, you have different kinds of planets which are observable. In terms of masses, this is an observational bias that most of the detected planets have masses greater than Jupiter, and essentially because planets with smaller masses are more difficult to detect with the Doppler technique. Like I told you, the wobble will be much smaller, so you won't be able to detect it. Hot Jupiters are composed basically of hydrogen and helium, and they could be as very close to their stars, and there are many more details about it. So as of now, there are. This is an earlier plot, but there are over 3,000. I told you 4,000, of which you can actually see that the bulk of them are Jovian, Jupiter-like. Mercury size of this 3,700, which was detected in 2017. 5 of them are mini-terrain, 72 are about Mars size, 701 are Earth size, 982 are super Earths, 799 are Neptune size, and 1200 is Jovian size. Like I said, when you look at these numbers, you have to always keep in mind the observational bias. So if you actually see this, this should have given you this. As of January 2, 2020, these are the total amount of planetary systems which have been detected. Right? So actually a video which is not playing. But okay, no problem. And now there's a big boom which is coming in with the launch of the James Webb Telescope. So amongst the first light images of the James Webb Telescope, you had images. These are of exoplanets, right? So you can see over here, you can actually see these exoplanet systems. This image actually shows the exoplanet Hipparchus 65426b in infrared. Purple shows the NIRCam this thing, and various images which were available using this. So this is the first direct image using Webb. What else can James Webb do? What James Webb can do very well is it can actually look for water. It can study the atmospheres of these exoplanets, as well as look for various other molecules, carbon dioxide, sodium, more, and look for a very good biosignature is methane, which actually tells you about the existence of potentially habitable worlds. And this is one of the images for the first light images. This is not a Webb image. This is an image which is showing you the transit light curve of WASP 96b, and this was a known exoplanet. But what Webb basically did is it did the spectroscopy of this planetary system, and it actually detected water on this planetary system. So this was the last of the first light images of the James Webb, which was actually this graph, which was this plot, which was basically of the atmosphere of the exoplanet WASP 96b, which clearly shows you the existence of water. So what James Webb can actually do is it can actually detect various carbon dioxide on exoplanets. It can detect water. James Webb also has a coronagraph, so it can do what I was showing you, the direct imaging, the example also I showed you, and it can also characterize various of these things. But obviously what needs to be done is you actually need to get candidates by using Kepler data, test data, and various other citizen science campaigns with which you can actually identify exoplanets. And then what James Webb can do is it can then observe the atmospheres of those planets and characterize them. And in some cases, not all, it can actually try doing some kind of direct imaging. And therefore, I'd like to wind up with this, that the future is definitely bright. You have a lot of stuff coming in with James Webb itself. If you look into the news, there's all the time something happening with James Webb. There's some new images coming. There's also the Nancy Grace Roman telescope, which will be launched in 2027. There's the Euclid telescope, and there's possibly also going to be the Super Hubble, which will be a much larger telescope compared to the older Hubble. And therefore, there's a lot of new developments which we expect in the field of exoplanets, making it a very interesting and a very important topic of research in astronomy in today's times. So I'll wind up with this, and I'd be happy to take some questions. Yeah, sure. Yeah. Yeah. No, diffraction will anyway take place because light is a wave, right? So you are going to get diffraction. Diffraction anyway will take place because light is a wave, right? But the idea in the transit method is basically to find the fall in the brightness. See, this is the typical method which is also used, for example, for binary stars. You look for a dip in the brightness, but that could be caused because of two stars. In this case, the dip is coming because of the planet coming in front of the disk of the star, right? So, so is that what would be? Yeah. So what do you mean by the diffraction effect? Yeah. Yeah. In that sense. No, no, no. You won't get that kind of an effect. You won't get that kind of an effect because the scale at which it's happening is very different. You're looking at optical light, right? And the size of the planet is much larger than the wavelength of light, right? See, for diffraction is basically observable if the size of your obstacle or your slit is comparable to the wavelength of light, right? Now, in this case, you will not have that kind of an effect coming, right? Because the size is much larger. So, no, you will not have that kind of an effect. No, so at the edge, what they do is this what they call transmission spectroscopy, right? When that edge part, then what happens is the sunlight, the starlight passes through the atmosphere of the exoplanet, right? And that is the basic method which is called transmission spectroscopy to characterize the atmosphere of the planet, right? But you don't get a diffraction effect. You do not get that. No. But that's an interesting thing, but it doesn't come with. Yeah. What do you mean by latest project? No, there is one called Planet Hunters. There are quite a few projects going on. So if you're in touch with Sovamacharya sir, he has this citizen science group of his, right? So there is one called Planet Hunters. You can Google it and look for it. And yes, that is in citizen science. But otherwise, if you want, you need to directly analyze Kepler or test data, and that could give you results. So there could always be something that has been missed out by people because the amount of data is so much larger, yeah, than the number of people working on it. Yeah, yeah, welcome. Uh, Yeah, no, but this one is a physical one. This is a physical one because otherwise you have to somehow cut off that light. But I think I'm not too sure, but I think it's a physical one. Yeah, 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 yeah. Yeah. So thanks, good question. But it basically it'll show up in the transit curve. So if you had a single planet, you will get a single dip. Typically, if you had say two, you would get say one dip and you'll get a second dip, and the size of the dip will basically tell you, like I told you, the ratio of the radii of the planet to the star, right? So for example, if you had two planets of different sizes, you will get two different dips, right? But obviously, the whole thing depends upon the kind of ratio of the orbital periods of both these planets, right? So it's a little tricky thing, but it actually is done, because in many of these cases you do have more than one planet going around the star, right? And the most probably that will cause most of them will have different orbital periods, right? And therefore, when I showed you that Kepler light curve, right, which very nicely put dips, you will actually observe the dips not coming very evenly, or you'll see some further smaller dips, right? And then people actually fit that properly and actually look for for multiple planetary systems. Yeah, so that's right. That's right. So you can. It just depends upon their sizes. So Arjun Ghosh, I actually googled and checked, and actually said that the coronagraphs are basically hardware. They're actually a set of mirrors, etc., and do that. It's not done through software. They actually do it through hardware. They are mirrors. Yeah, so Tejendra Pal saying that's right. So also, if you have more than one planet, if they have satellites, all that should show up in your light curve. But the problem is that then your accuracy of the photometry should be so good that you are able to see these multiple dips coming because of different planets and their satellites, etc. But because the problem is, even getting one planet is like you want a 1% dip, right? So then if you want to get more, you need to get that really accurately and well. But yes, it is done, and people do find multiple planets through systems. Like, for example, the TRAPPIST system, right? The TRAPPIST 1 system, which you'd heard about, you have 7 exoplanets in that. And it's essentially by looking at the light curve. Yeah. For what, sorry? For what? Okay. Okay. Yeah, I don't see anything in the chat. That's it. It definitely has a high probability. Yeah. Yeah. Yeah, yeah, sure, sure. Sure. Okay. Thanks a lot. Thank you so much. Yeah. Bye bye. Yeah. Yeah. Bye. Thanks. Bye bye.
Bye.
Bye.